Hello. This is Nicholas, and I wanted to just do a video on the multivariable chain rule. I kind of hinted at it in the last video with the tangent planes. And so it's really just a natural extension of the chain rule from Calc 1, which is also just a special case of the multivariable chain rule. And so the idea is that in Calc 1, we just had functions like, say, f or y, whatever you want to call it, which then depended on x, and then we could say maybe x depended on some other variable t, and then maybe t depended on some other variable u. And so if we were to differentiate f with respect to u, or I'm already doing partials. If we were to take the partial derivative of f with respect to u, and we would be taking it with respect to u since u is the innermost variable there, we would get the derivative of f with respect to x times the derivative of x with respect to t times the derivative of t with respect to u. And all that's due to the chain rule from single variable calc. So hopefully all I've said here is nothing new to you at all. Now what we're going to introduce is functions of multiple variables. So let's say we have a function w, and let's say that w is a function of x, y, and z. So w would actually be a four-dimensional like hypersurface because it has three independent variables and one dependent variable. So that requires a total of four axes all perpendicular to one another. But then we could say, well, what if x, y, and z are functions of u and v? And so we would probably ask, well, what's the derivative of w with respect to u, or the derivative of w with respect to v? So we have two kind of innermost dependent variables, right? Ultimately, our function depends on u and v in the end when we get to the bottom of this tree. So, and these tree diagrams are very helpful. I would recommend drawing them. So, for example, if we wanted to find the partial of w with respect to u, and we would have to do it with either respect to u or w, since we would have to do it with respect to either u or v, since u and v are our innermost dependent variables, and ultimately everything could be written as functions of u and v. So if we wanted to find the partial derivative of w with respect to u, what that would look like is we would find all the possible ways that we could go from w to a u anywhere on this tree diagram. And so how can we do that? We can either go w to x and then x to u, w to y and then y to u, or w to z and then z to u. And so what that looks like is we basically take the sum of multiplying along each of these branches. So what that looks like is we would have a partial of f with respect to x, or partial of w with respect to x, not f here, we're using w with respect to x. And then we would go along that same branch from x to u, so we'd have the partial of x with respect to u. And so we're multiplying there because we're going along that same branch. But now here we're going to add another pathway, so we're adding the partial of w with respect to y times the partial of y with respect to u. And so that comes from going from w to y and then y to u. So we're going along that branch, and so whenever we go along a branch, we're multiplying by our partial derivatives, and then when we go to another branch, we're adding that separate outcome. So that should be relatively intuitive, at least. And then now we add our final way to get to u, which is to go from w to z, and then from z to u. So partial w with respect to z times partial z with respect to u. And this would be dw over du by the multivariable chain rule. That's what you would have to then calculate. As a similar example, if we were to find partial w with respect to v, it would be very much the same. Literally the only difference you do is this u would become a v, this u would become a v, and this u would become a v. Everything else is still the same because it's still the same tree diagram. maybe one more example. If I have w just going from x to y, and then x is a function of t and y is a function of t, just kind of one thing I'd like to note. So ultimately, the only partial derivative here we can find is the partial of w with respect to t, because t is our innermost dependent variable, if you will, and ultimately everything could be written in terms of t. So that could be written as, we can go from w to x, and then from x to t. So for now, you don't see it normally written this way, but for now, I'm just going to write it as partial w with respect to x times partial x with respect to t, plus, so that this first part here comes from going from w to x and then x to t, and now we're going to go from w to y and then y to t. So we have partial w with respect to y times the partial of y with respect to t. And now I'm going to simplify this some, because realize that from x to t, there's only one way to go from x to t on this tree diagram. And so therefore there's only one direction of change that we are accounting for. And so when we're only changing along one axis or on our graph, we only need the normal derivative there. We don't need the partial derivative. In other words, the partial derivative and the normal derivative would be equal to one another, because we're only changing along one direction, and so all other directions are held at a constant anyways, because we're only going along one to begin with. So what I'm saying we can write is we can write partial w with respect to x times dx over dt, being the normal derivative, plus partial y, or plus partial w with respect to y times dy over dt. And it's acceptable to write it in this form, but it's more simplified in this form, because again, there's only one way to go from x to t and from y to t. So the partial derivative and the normal derivative would be equal at that point. Okay, so maybe as an example, let's say we have, I don't know, z being equal to the square root of x squared minus y squared. And then we could have x being equal to e to the 2t and y being equal to e to the negative t. The first thing I always do in these like multivariable chain rule problems is draw the tree diagram. The tree diagrams are very, very helpful, especially if you've got like 10 independent variables or something. So first of all, we have our original function z. Z is a function of both x and y. But then from here, we know that x and y are both independently functions of t. So then we know that, and we can only find one partial derivative here. We can ultimately only find our partial z with respect to t. And so we know that that's going to be equal to partial x, or my bad, I keep getting ahead of myself, partial z with respect to x times dx over dt plus partial z with respect to y times dy over dt. And so now what we can do is we can just find what these things actually are. So partial z with respect to x. So here y is the constant, and so we just have we would just have 2x over the square root of x squared minus y squared. Oh, we would have a 2. Because in general, if I had say y squared was 7, if I had the square root of x squared minus 7, and I were to differentiate that, then that would go to 1 over 2 square root. Wow, that's a horrible square root. 2 square root x squared minus 7 times the derivative of the inside, which would be a 2x, and so those would cancel. So yeah, we just have an x over square root x squared minus y squared. Now I need to take the derivative of x with respect to t. So that's just going to be 2e to the 2t plus partial z with respect to y by the exact same logic as y over the square root of x squared minus y squared. Normally, we would technically have a 2 and a 2, but then they cancel out. So now what we can then do is then take the derivative of y with respect to t, and so we're going to get a negative e to the negative t. And so when this is all simplified, we get 2x e to the 2t over the square root of x squared minus y squared minus y e to the negative t over the square root of x squared minus y squared. And that is about all you can really do there. Maybe, I guess, if you wanted to combine them, you could write them as 2x e to the 2t minus y e to the negative t all over the square root of x squared minus y squared. And that would be your answer there that you would leave. You might be thinking, well, why don't I replace all my x's with e to the 2t's and then go from there? Well, you can, but it's not really necessary because we already know that x is e to the 2t. So it's fine having both x's and y's and t's all in here for your partial derivative of z with respect to t. And technically, this wouldn't even be a partial derivative. Dz, it would really just be dz over dt. Because, and it wasn't wrong of me to write partial of z with respect to t. But again, since we ultimately only had one independent variable, or one innermost variable, like it's at the bottom of the tree here, our t, then we're only going to have one possible derivative that we can take of all of this stuff, and that's going to be with respect to t. So the partial and the normal derivative would be equal in that case. Maybe one more example. If I have, I'm getting these from my journal. If I have z equals x squared y minus 3xy cubed, but then I say, well, x is a function of u and v, so x is u squared minus v squared. And then I say y is also a function of u and v, so y is 3u plus v. And I want to find all the different partials that I can possibly take, so with respect to u and with respect to v. So if we draw this out on a tree diagram, which I would recommend you always do first, we have x and y. Z is both a function of x and y. But then x is a function of u and v, and likewise y is 2. So we have two partials that we need to find here. We need to find partial z with respect to u and partial z with respect to v. So partial z, and they are indeed partials here, they're not normal derivatives, because here we have two innermost independent variable, or two innermost, I don't know why I keep saying independent variables, two innermost dependent variables, and those would be u and v. They're at the bottom of this tree. And the ones at the bottom of this tree are always your innermost dependent variables. So partial z with respect to u, that's going to be equal to partial z with respect to x times partial x with respect to u plus partial z with respect to y times partial y with respect to u. So we're taking basically along this tree diagram all possible ways we can get to a u, which is those things that I've done in the laser pointer. And then likewise, very similar logic, partial z with respect to v is partial z with respect to x times partial x with respect to v plus partial z with respect to y plus times partial y with respect to v. Just literally all I did was replace the u with the v's here because it's the same tree diagram. And so now we need to calculate what each one of these are. So first of all, partial z with respect to u, that's going to be partial z with respect to x. So that's going to be 2xy minus 3y cubed times partial x with respect to u, so that's just a 2u, plus partial z with respect to y, so that's plus x squared minus 9xy squared, times partial y with respect to u, which is just a 3. And I'm going to let you simplify that. I'm not going to go through the algebra. I know you can do that, but that's the idea there. And so now likewise, partial z with respect to v is going to be partial z with respect to x. And so that's going to be the same thing. That's 2xy minus 3y cubed times. Now we have partial x with respect to v. So that's going to be a negative 2v. Plus partial z with respect to y, that doesn't change. That's still x squared minus 9xy squared. Times partial y with respect to v, which is just a 1. And so those are all the possible different partial derivatives we can take with respect to our 2 innermost dependent variables. And that's all what the chain rule is all about. I hope you found this helpful.